Expressions for the frequency at which the maximum voltage occurs across the inductance and capacitance in series resonance circuit, or otherwise variation of current and voltages across L and C with the frequency of series resonant circuit. So here first let us draw the diagram of series RLC circuit. So that is the first point. So series RLC circuit. So resistance, inductance and capacitance connected in series, and this combination is connected to a voltage source. Once this combination, this circuit, RLC circuit is connected to a voltage source, there is a current in the circuit. Next, so let us draw the waveforms. So second point, so here we get waveforms. So waveforms against frequency. So F is on x-axis, and here so this is the current waveform. So in series RLC circuit, how current varies with respect to frequency. So as you go on increasing the frequency from 0, current increases up to resonance frequency. So later on, for any increase in the frequency from FR, that is resonance frequency, current decreases and it goes to 0. So at resonance frequency, current in the circuit is maximum. So similarly, if we draw voltage across the capacitor waveform, so this is the voltage across the capacitor waveform against frequency. As you go on increasing the frequency, so voltage across the capacitor increases to maximum value and then decreases. At one frequency FC, so voltage across the capacitor is maximum. Now we have to find the mathematical expression for this frequency. So similarly, if we draw voltage across the inductor waveform against frequency, so the curve looks like this. So this is the VL, voltage across the inductor against frequency. So it increases to a maximum value and then decreases. So maximum value, the corresponding frequency, let it be VFL. Now we have to find what is the mathematical expression for this FL, such that voltage across the inductance is maximum. Next, so frequency at which maximum value of VL occurs. So here first we are finding this mathematical expression for this FL, frequency at which voltage across the inductance is maximum. So here again frequency at which maximum value of VL occurs. So the voltage across an inductor is given by, so in general voltage across the inductor is nothing but so VL equal to I into XL, current into reactance offered by the inductor. So which is equals to I into XL, reactance offered by the inductor is equals to omega L. So let it be equation 1. So current in the circuit is equals to voltage by impedance offered by the circuit, V by Z, which is equals to V by, so if you take magnitude of the impedance, so which is equals to root R square plus omega L minus 1 by omega C whole square. So let it be the second equation, equation 2. So now substituting equation 2 into equation 1. So we get VL is equals to V omega L by root R square plus omega L minus 1 by omega C whole square. So let it be equation 3. So here we have to find the frequency at which VL is maximum. So for that, to find the frequency FL at which VL is maximum, use condition of maxima, that is dVL by d omega equal to 0 at FL. So here at maximum conditions or minimum conditions, differentiation of that variable with respect to x variable. So differentiation of y variable with respect to x variable is 0. So here y variable is VL and x variable is omega. So differentiation of VL with respect to omega is 0. So that is the condition of maxima. So VL square is maximum only when VL is maximum. So here we are finding for VL square. When VL is maximum, VL square is also maximum. So VL square is equals to. So from this expression VL is this. So we are squaring of this. We are eliminating the square root by squaring on both sides. So VL square is equals to. So VL square is equals to V square omega square L square by R square plus omega L minus 1 by omega C whole square. So here we get whole square. So here we are eliminating the square root by squaring on both sides. So if we simplify this, we get V square omega power 4 L square C square by omega square C square R square plus omega square LC minus 1 whole square. So finally if we simplify still, we get VL square is equals to V square omega square L square C square by omega square C square R square plus omega power 4 L square C square plus 1 minus 2 omega square LC. So take this as equation 4. So here now by differentiating VL square, now we have to differentiate this VL square with respect to omega and we have to equate that to 0 for the maxima condition. So by differentiating VL square with respect to omega and letting dVL square by d omega equal to 0. So first we have to differentiate this dVL square by d omega, we get this and we have to equate this d0. So we have to go on simplifying this equation. So finally we get omega square equal to 2 by 2 LC minus R square C square, which is equals to 1 upon LC minus R square C square by 2. So if we extract omega, therefore finally omega L, so that is frequency in radians per second at which voltage across the inductance is maximum is 1 upon root LC minus R square C square by 2 radians per second. So if we know the values of RLC, resistor value, inductor value and capacitor value, so we can find frequency at which voltage across the inductance is maximum in radians per second. Similarly, so we have to find frequency at which maximum value of Vc occurs. So voltage across the capacitance is maximum, then what is at which frequency the voltage across the capacitance is maximum. So the voltage across capacitor is given by Vc is equals to Ixc, which is equal to I. Xc is 1 by omega c. So let it be equation 6. So substituting equation 2, substituting equation 2 into equation 6, we get Vc is equals to V by omega c into root R square plus omega L minus 1 by omega c whole square. So for maxima Vc, so we have to differentiate Vc with respect to omega and equate to 0. So here if we see in Vc, so there is a square root. So to eliminate that, instead of Vc we are taking Vc square. So dVc square by d omega equal to 0. So first we have to get expression for Vc square. So Vc square is equals to, so this is Vc, squaring on both sides we get Vc square. So Vc square is equals to V square by omega square C square R square plus omega square LC minus 1 whole square. So if we simplify, we get this mathematical expression for the Vc square. Now differentiating that Vc square with respect to omega and equating to 0. So we get dVc square by d omega, which is equals to, so if you differentiate that Vc square with omega, we get this expression and we have to equate that to 0 and go on simplifying this. So finally we get omega square is equals to, so 2L minus CR square by 2L square C, which is equals to 1 by LC minus R square by 2L square. So finally omega C is equals to root 1 by LC minus R square by 2L square. So radians per second. So this is the frequency in radians per second at which voltage across the capacitor is maximum. Voltage across the capacitor is maximum. So here we derived two expressions. So what is the voltage across the inductor? What is the frequency? At which frequency voltage across the inductor is maximum, that is FL. In radians per second it is omega L. So similarly omega C. So that is the frequency at which voltage across the capacitor is maximum.